Welcome, colleague. I am Ho Yun-jun from BOS Semiconductors, presenting our automotive design verification methodology. The exponent growth in the SoC complexity coupled with the automotive safety requirement has elevated verification to a critical engineering discipline. I will present our structured approach for delivering functionally verified automotive silicon. As a fabless semiconductor provider for automotive applications, we implement verification protocol that acknowledge direct impact on vehicle safety system. Our chip interface with critical control unit where functional anomalies cannot be tolerated, necessitating comprehensive verification methodology. My presentation will detail our feature-driven framework across the four technical domains: verification flow architecture, hierarchical planning methodology, test bench optimization technique, and quantitative closure metric. These components operatively cohesively to identify functional and performance defect for silicon. In automotive semiconductor development, where Asian compliance is mandatory, our verification processes are designed to meet these stringent requirements. In this presentation, I will describe four core components of BOS Semiconductors verification architecture that ensure our automotive chip meets critical safety standards. We will begin with our verification flow framework, a traceable process from initial feature extraction through the final sign-off. Subsequently, I will detail our feature-driven verification planning methodology, which systematically transforms vision requirements into hierarchical verification targets across block, subsystem, and SoC integration level. The third component encompasses our test bench architecture strategy, which implemented strategic abstraction technique to optimize the inverse relationship between verification thoroughness and simulation performance. Critical consideration for automotive SoC with simulation runtime measured in hours. Finally, I will present our verification closure framework with quantitative metrics that establish deterministic production readiness criteria. These four interdependent components constitute comprehensive verification system that ensure functional correctness while maintaining traceability to automotive safety requirements throughout verification life cycle. Let me now describe our 7-stage verification architecture illustrated in the process flow diagram. Stage 1. Verification request. Verification engineer extracts verifiable functionality from the specification and design document. These documents are reviewed by the designer and the verification engineer to ensure comprehensive scope definition, establish verification boundary conditions. Stage 2. Verification plan. Verification engineer decomposes the functionality into the test item with the coverage point and assertion criteria. This plan undergoes cross-functional review with the design engineer to ensure architect alignment. Stage 3. Test bench building. We map test requirements to verification environment using our UVM platform, integrating standardized components including rest model and initialization sequence to ensure environment reusability. Stage 4. Scenario writing. Engineers implement direct and constrained random test sequence with sample checking mechanism and protocol monitor, establishing automated bug detection infrastructure. Stage 5. Run and regress. We execute the test sequence with randomized seed, analysis failure, and implemented regression testing to ensure deterministic behavior across simulation conditions. Stage 6. Coverage corrosion. We aggregate functional, toggle, and code coverage metrics, developing target tests to address identified coverage gap in the verification matrix. Final review. We conduct a comprehensive review against all verification checklist items before mask tape-out, ensuring complete requirement fulfillment. Our methodology is founded on two principles: verification completeness. We implemented systematic peer review throughout the verification lifecycle because a single verification escape can result in $1 million risk spin and market delay. Process automation. Following planning, we automate test generation, regression, and coverage analysis to optimize resource and eliminate human error in repetitive tasks. At BOS Semiconductor, our verification methodology employ a feature-driven planning approach. Feature in our verification context represent the specific functionality or characteristic requiring verification against the defined observed criteria. To illustrate this concept, consider the HDMI to the 1B interface depicted in our technical diagram. One critical feature is the 48 gigabit per second bandwidth specification, a parameter enabling 8K at 60 Hz or 4K at 120 Hz video transmission. This feature manifests in hardware via the three signal categories transmitted from the SoC logic to the HDMI to the 1B transmitter. Video signal contain the actual feature data, audio signal for sound, control, and status signal for the measurement. This signal travel TMDS to 48 gigabit per second, aggregate bandwidth to support 8K video data requirement. This bandwidth specification qualifies as verification feature because it has explicit specification requirement, include quantifiable acceptable criteria, required function verification, represents a potential critical failure mode effect and product functionality. Effective verification architect required systematic feature categorization. As illustrated our hexagonal taxonomy diagram, we classify feature into the 6 domains. First, functional capability, core operational requirement, interface behavior, intercomponent communication protocol, special mode operation, debug, test, diagnosis function, performance characteristics, bandwidth specification, error handling mechanism, exception detection and recovery, power management, state transition, and consumption parameter. This visual classification methodology applies hierarchically across component, block, and system-level verification, ensuring comprehensive coverage across the design hierarchy. Let me first articulate the fundamental challenge in SoC verification. Contemporary automotive SoC integrate heterogeneous subsystems, multiple process clusters, FeatureDriven interface, communication protocol controller, functional safety module, and domain-specific accelerator. Full system RTL simulation with all components fully elaborate result in prohibited execution time. A single test can take hours or even days for compute time, rendering comprehensive verification practical within development cycle constraint. Our test bench architecture stretch address these constraints through the strategic abstraction. As illustrated in our technical diagram, we implement SoC-level verification environment with dual criteria, configured to match target verification item. Each test bench configuration is precisely tailored to target specific verification objective, optimized to minimize simulation time while avoiding bug escape. We implement abstraction technique that minimize execution time while maintaining verification coverage. The core implementation technique is component stopping, selectively replacing the specific RTL module with behavior equivalent. This abstraction model consists of fake RTL implementation with functional equivalent interface and functional model as known as transit. This module is yield the significant performance optimization while preserving functional equivalence. The VFM accurate replicate interface behavior of the original RTL module without executing the computationally intensive microarchitect implementation. While primarily deployed for processor subsystem, this abstraction technique extends effectively to other subsystems and subordinate IT like memory system, enabling simulation performance improvement. Let me now address our implementation of the save and restore technique to optimize the verification efficiency. This methodology significantly reduces simulation runtime for the complex SoC verification environment, as illustrates the upper section, our technical diagram, the conventional simulation methodology necessitates a complete simulation cycle for each test system initialization phase. These include the process subsystem boot sequence execution, clock configuration, memory control initialization, and peripheral setup operation. In our example, while functionally identical across test case, this phase consumed approximately 2/3 of total simulation runtime. Functional verification phase, the test-specific portion that exercise the target functionality. In our example, single verification cycle requires the 3 time units. Consequently, executing 4 distinct test cases necessitates 12 T of the algorithm sequence time. The lower section of our diagram illustrates the save and return implementation. We execute initialization sequence once, consuming 2T, and generate the simulation state checkpoint at the initialization boundary. For each subsequent test, we restore this preserved state and execute only test-specific verification portion, 1T. This methodology yields an aggregated simulation time of just 3T. This approach delivers the quantitative 50% efficiency improvement in our example, with the optimization factor increasing proportionally with the test quantity. Finally, let me address our quantitative verification closure framework and sign-up criteria. This methodology provides deterministic metrics answering the critical question: what constitutes a sufficient verification for production release? Our coverage-driven verification strategies implemented the multidimensional measurement system, quantifying verification thoroughness. It illustrates in our hierarchical diagram, we employ the 3 complementary coverage domains. Test coverage. This top-level metric quantifies the verification plan, execution completeness, tracking successful execution of all planned test cases. While conceptually straightforward, this metric ensures verification plan implementation traceability. Functional coverage. Functional coverage directly correlates to the feature-driven methodology discussed earlier. This represents our most critical coverage domain as it establishes direct verification mapping to product specification and architecture requirement. Code coverage shown on the right branch with the 5 sub-classifications. Code coverage measures the actual implementation exercise during the verification execution. This provides complementary perspective to functional coverage by ensuring implement-level verification thoroughness. Our release qualification mandates 100% coverage attainment across all metrics, and we implement wave items only for demonstrably unreachable coverage conditions with comprehensive review documentation. This concludes our presentation on BOS Semiconductor Verification Methodology for automotive grade SoC. Thank you for your attention.